We received a request from the program managers and the exec to evaluate the possibility of installing a diverter in ST40.
Typically, in a national lab, a diverter would be a multi-year project to design and build.
It's the first time that we know that a diverter has been designed and procured and installed so quickly.
When ST40 reached its 15 million degree milestone, it was operating with the plasma in what's called a limited configuration. The plasma was almost circular, with limiters, like car bumpers, preventing the plasma from touching the walls. We talked about how diverters are used to manage the heat and power from the plasma in a previous video. They are the exhaust system of a tokamak, and they allow us to achieve much higher levels of performance. In 2019, the Divertor team was designing a diverter for a future major upgrade of ST40. But then, in 2020, it was decided to fast-track a diverter into the current ST40 without a major upgrade, in order to improve performance for the 100 million degree milestone. It was always going to be a huge challenge, but then coronavirus struck as well. We talked to Daniel Iglesias, the Divertor team leader, and Rob Bamber, the realization engineer on this project, to find out more.
We got a big milestone in ST40 in the following campaign, which is achieving 100 million degrees in the plasma. The risk of achieving that is less when you run a diverter configuration. So we're doing all that we can to put power to heat the plasma up. The reason to have a diverter is to minimize the losses of the plasma.
A diverter plasma is a different configuration. So you have a different magnetic configuration, you pull the plasma up and down. And this tends to give a waterfall of particles around the sides, which keeps the core plasma clean and stops the radiative heat losses.
We made a very quick feasibility study in 3 days. We decided that it could be done.
4 months, I think the target was at the time. This was very, very tight schedule. We did it in about 6 months, but we had the COVID pandemic, which obviously didn't help.
The objective was to get in time with something that was good enough. Of course, while you are in the design process, you always spot things that you can improve. We limit ourselves to very strict deadlines, and we froze several features in the way, and then we wouldn't look back. There was another driver, that is to be able to run the machine at different magnetic fields. So the wider that operation range, the better.
This diverter is around 40 megawatts per meter squared. It's a short time, which is the saving grace. But to put that into context, big coal-fired boilers that you feel the high heat fluxes there are about 0.5 megawatt per meter squared. So that big roaring fire is, we're about a factor 80 higher.
Although the timeline for the diverter was relatively short, the team had already laid a lot of groundwork for the project in 2019.
We have planned and we have in design a high-performance diverter. So we used the development that we had. So we were starting from scratch from the design point of view, but we had already developed technologies and manufacturing techniques, and we had tested the performance of some concepts. We decided to put them together in a very different design, because this is half the power and for 10 times less duration, so the energy is 20 times less, so it can have a simpler shape.
So this is the testing that we were talking about. This testing was undertaken for IVC2, and you can see we had 28 different combinations. So we used 2 different copper alloys as a substrate, GlidCop, which is oxide dispersion hardened, and copper chrome zirconium, which is precipitation hardened. Some of these are tungsten tops, some of them are molybdenum tops, and you can see here through the different heat cycles, we did 100 cycles. This is at the beginning of the runs, and you can see not a lot of sort of damage in the middle of the day, and then at the end of the day. This sample H is the molybdenum copper chrome zirconium alloy, which we have selected for use. Last year we were preparing for the next IVC and the diverter on that with the larger tiles, and because we had many material combinations to test, we used 35mm square samples to reduce the costs on the initial prototyping stage. So because we'd started prototyping for the next inner vacuum vessel diverter, we were able to piggyback a lot of that work and consequently save time and cost on the development.
With the challenge laid down to the team to create the diverter in just a few months, the project required collaboration from across Tokamak Energy to achieve this rapid turnaround.
The main constraint was the timing, so we tracked back how much time we needed for different stages. And that left us with 1 week for the conceptual design stage and just 3 weeks for the detailed design stage.
My job was to take the design from Dan. So Dan's design typically gives the position of the tiles in space, how they shadow each other to stop the hard edges getting a flux, things like that. And my job was to work with the design office to see how we would mount all these things together, how we would hit all the other requirements. So I coordinated between physics and the drawing office about where we could physically put this in space versus where the physicists would ideally like it in space.
1 week later, we had an internal review of the different concepts that we have thought about, the different requirements that we wanted to put together. That was approved by all the responsibles. And then 3 weeks later, we arrived with detailed design, which was not only internally checked, but we also invited international experts to do an evaluation and further recommendations on. And it got the green light for starting the manufacture. We also incorporated some of the advice that we received internally and externally.
This is a model of 1/8 of the diverter. The top view here, you can see the upper small collar that we have. This is a cutout to allow it to go around the limiter. At the bottom here, you can see what we call the large collar, which is made in 8 sections, and you can see a joint and how they're bolted together. And this modelling basically lets us estimate the stresses in the components and determine if it's fit for service or not. So if we have a look here, we can see the predicted movements of around 200 microns, 250 microns at this level here. And the stresses in the components are very, very low, less than 100 megapascals in the copper and less than 150 megapascals in the stainless steel components.
With the design complete, the manufacture of diverter components was affected by the coronavirus lockdown.
The ideal for a project like this would be to use one supplier, but there were things that were split between multiple suppliers because a lot of them came back to us and said, we want to help, but we can't do it on the time scale. We say, okay, well, can you do this bit? And we'll find someone else to do that bit. And we used around 25 suppliers. But one thing that comes up is most of them are very local suppliers in a 50-mile radius. And that means that we can go and see them. If there's a problem, we go to them.
Installing the diverter with over 5,000 components would ordinarily be a lengthy process, involving the disassembly of the tokamak, which would take months. Instead, the team devised a novel solution to this problem.
The idea here was to go in and install everything through a port.
So this is a mock-up. It's a 1-to-1 scale replica that has been 3D printed of the inner vacuum chamber of ST40. We used it for practicing the installation of the in-vessel works that we did in this summer.
ST40, because it uses cryogenic copper magnets, it's got a vessel in the outside that provides the cryogenic insulation. Then we got the toroidal coils inside of it, and inside this toroidal field coils, we got some of the polyoidal field coils, and inside we got the vessel finally. In order to install something inside of the vessel, what we typically do is pull everything apart, but that's an operation that takes 6 months. And we didn't have that time, really.
The diverter itself is a set of plates that goes here. The strike plate on this design is 2 collars that come round, and structurally they attach here and here to the vessel to support the electromagnetic loadings. And we have 528 tiles which are mounted in this region. And we went in to practice the assembly. All the access was through a hole that was about this size, and this was built specifically to allow us to practice. So this is one of the tiles. This is a spare tile. The way we made them, this is 4mm thick molybdenum on the top, and it was water jet cut out of a large sheet. The chamfer was put on a milling machine. These were then sent off, and we used electroless nickel plating on the inside. The electroless nickel is a nickel phosphorus, which acts as a braze alloy, and it was then brazed to the copper alloy base, which had been CNC machined. The whole thing is then nickel plated to prevent having copper exposed to the tokamak vacuum. The job was very difficult for 2 reasons. The inner vacuum vessel normally operates at around 10 to minus 8 millibar, which is what is called an ultra high vacuum. And so this needs to be very clean. Guys have to wear gloves, they have to wear overalls. Added to that is the confined space issue here. So obviously this is around about 2 meters diameter. There's a central column that comes all the way up here, and the space inside for the guys is very, very tight. The access was through a single hole this way. For safety reasons, we had a second hole on the other side opened, and the job was treated like a confined space with a guy standing on the door whenever anyone was in vessel. So the guys, they crawled through the hole into the vessel. They would sit. So what's missing on this mock-up? There's an MC coil which sits about this high. It's very strong, so they can support their weight, and goes right round. And they would sit on that and be in vessel for around an hour and a half or 2 hours at a time. The mock-up we used to practice fitting things in, to make sure the whole thing fitted together well. We found a couple of small errors on the machining on the mock-up trials where threads weren't deep enough, and because we did this a couple of weeks before the installation, we had time to rectify the problems and make the installation run relatively smoothly. Everything goes better with practice, as the Boy Scouts say.
Everyone was doing their best, really. There were issues, of course, but yeah, at the end, we were able to install it, and we're really, really looking forward to see it work.
The ST40 diverter upgrade is a proud moment for Tokamak Energy. And now, with the BioShield installed, we're looking ahead to a new phase of testing with increasingly hot plasmas as we move towards 100 million degrees.
It's more than proudness. It's been really a pleasure. It's been a pleasure to go through this project. It's been a pleasure to work with everyone and see everyone so committed. And it's really been fantastic go from the drawing board to see actually happening and get these wonderful pictures of how it's installed, and it's exciting to see how it actually performs, and we're gonna know it pretty soon.